Hello, AP Stats students. Mr. Hazelhorst here with your Chapter 8, Section 2 video. Today we're going to talk about the geometric distribution. So first two videos focused in on binomial. Now we're going to change things just a little bit. So let me give you an example of a geometric distribution problem, and I want to see if you can notice what might be different here. Okay? So here's our question. It says you take a 15-question multiple choice quiz, 5 choices for each question, and completely forgot to study, so you decided to guess. The question is, what is the probability that you don't miss a question until number 5? Now, if we look at this problem, and let's say we treated it like a binomial to start, we'd have to answer a couple of questions. First off, do we have only 2 outcomes? Hopefully we'd say yes to this. You either get the question correct or incorrect. Fixed number of trials, yes, we have 15 questions, and they're independent, okay? But what's different about this is when we look at the question that's being asked, right? This question is not dealing with all 15 questions in the quiz, but it's dealing with a specific outcome happening up until a certain question, right? So if we look at it, it says, what is the probability that you don't miss a question until number 5, okay? So in this, it's not binomial because we're not looking for a certain number of successes, but what we're looking for is when that first success occurs. Now, we're going to start out by actually calculating this probability just to illustrate that we really don't need a rule. We really don't need a formula. Something that fits a geometric distribution is really just a lot of common sense, okay? So if I were going to find the probability in this question, all right, we need to recognize we're just looking at the first 5 questions. And what we want to have happen in this setting is we want to get it correct, 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 and then on number 5, we finally miss our first question, okay? So if I look at this setting, what's the probability that I get a question correct? Well, it's 20%. So for all of these problems, it's 0.2 on the first 4, right? The probability I get the first question correct is 0.2, second 0.2, third 0.2, fourth 0.2, and then I miss a question. And I'm very specific about when I want that to happen and what is going to happen. So the probability that I miss a question is 0.8. So based on this setting, a little common sense tells me, okay, well, I'm just going to multiply all these probabilities together. And according to just this simple setup, basically using the multiplication rule for independent events, we see that our probability of not missing a question until number 5 is 0.00128. So an extremely small probability of that occurring, but that's a geometric distribution, right? A geometric distribution is very similar to a binomial. We're going to have the same characteristics. We're going to have only 2 outcomes. We're going to have a fixed number of trials, and we're going to have independent events. But what we're interested in is when the first success happens. So let's summarize that on a slide here. All right. So a geometric distribution is used to find the probability that it takes a certain number of trials before we obtain a success. Okay? And again, we still have those same characteristics. We need only 2 outcomes, success and failure. We need independent events. And what changes is the variable of interest, right? We're no longer interested in a certain number of successes, but a certain number of trials before we get our first success. All right, so this is why we put binomial and geometric distributions together in the same chapter, because again, they're very much related to each other. And hopefully you can see that as we look at our example and we look at the characteristics here. All right, so let's jump into a little bit more about geometric. So let me give you some settings. All right, so if you take a look at this list, I want you to analyze and say, all right, which one of these would be considered geometric? All right, so it meets our characteristics. There's only 2 outcomes, there's independent events, and there's a variable of interest as a number of trials, okay? So let's take these one at a time. So the first situation we have is that you flip a coin until you get a head. Would you consider that geometric? So let's answer the question, all right? Do we have only 2 outcomes? Yes, we do, right? Head or tail. Do we have independent events? Well, yes, we do, right? We know that flipping a coin is independent from one flip to the next. And our variable of interest is how many times you flip a coin until you get ahead. So yes, this would be considered geometric. It meets all three of our conditions. All right, how about number 2? You roll a die until you get a 3. Now, some people say, well, this is not geometric because there's more than one outcome. But all I really care about is that I get a 3. So I either get a 3 or I don't. Okay, so it's still only 2 outcomes. We know a die is independent. And again, we're waiting for a certain number of rolls. So yes, this would be considered geometric. All right, how about number 3? You draw cards from a deck without replacement until you get an ace. So if we just start drawing cards out of a deck, right? There's only 2 outcomes. You either get an ace or you don't, right? Number of trials is our variable of interest. But the problem here is we do not have independent events. Okay? We have dependent events. Right? Because we are dealing these cards without replacement. Now, if we said with replacement, if we drew a card, put it back in, shuffled it up, right, then we could say that, yes, this would be geometric. But again, we're dealing these cards without. Right? So how about this problem? In basketball, you shoot free throws until you miss. Right? Well, this would also be considered binomial. But what I want to point out in this problem is something that is unique in this problem, and that's what are we considering a success? Now, normally in basketball, if you're shooting free throws, you consider a success a make. But in this problem, what we're considering a success is a miss, because that's what we're asking about. And remember what we talked about when it comes to a binomial distribution. We don't want to think about success as how we normally think about success, right? Our success in a situation is just what we want to happen. And in this case, we're looking at how many free throws we make until you miss. All right? So that's something we want to keep in mind as we move forward in a future example on this presentation. Okay? So once we can recognize when something is geometric, then we have a set of formulas that we can apply to help us out with that. Okay? So this is our formula for a geometric situation. And what's important to recognize here, again, if we go back to the very first slide of this presentation, we didn't need a formula to calculate the probability. We could use common sense, okay? And that's what this formula is illustrating. So it says if x has a geometric distribution with the probability p of success, and then 1 minus p would be the probability of failure, okay? So if I'm looking for success to occur on a certain number of trial, right, I just take the probability of failure, meaning what I don't want to have happen, and I multiply that probability n minus 1 times, right? If I go back to my first slide, right, we wanted to figure out what was the probability that you don't miss a question until number 5. So in that problem, we were considering missing a question a success. So we went 0.2, 0.2, 0.2, 0.2, right? That was our probability of failure in this case. Again, success and failure being opposite of what we normally think. Now, on your graphing calculator, this is also built in. This is built in as the geometric PDF. Now, notice the order in which we will input things in our graphing calculator. We will input it as the geometric PDF, and then we put the probability of success first and the number of trials second. This is different than how we input things with our binomial, so we want to make note of that. Now, I should also make note that we also have a geometric CDF built into our graphing calculator. And we need to remember CDFs in our graphing calculator are set up for those at-most situations. So we'll look at an example where we'll use both the geometric PDF and the geometric CDF. Now, the other formulas that I want to make you aware of are the formulas for finding the mean and the variance of a geometric setting. Okay? So these are formulas that you'll definitely want to put down in your notes. I would recommend you write them in your gold packet. If you don't do it today, we will take time in class on Wednesday to put these formulas down in your gold packet. All right, but the formula for the mean of a geometric setting is just 1 over the probability of success. Now, if you stop and think about this for a moment, that should make sense, okay? If I asked you, how many times would you expect to flip a coin before you got ahead? My guess is you would answer 2. okay, which is the reciprocal of the probability of getting ahead, right? Probability of getting ahead on any given flip of a coin is 1/2. So we would expect that it wouldn't really take us on average more than 2. Okay, and so if we stop and think about it, that's hopefully a formula that makes sense. All right, geometric, just like binomial, is a lot of common sense in kind of how they work. Okay, so let's keep that in mind. All right, let's look at an example problem to finish out today's video presentation. All right, so let's say a 78% free throw shooter is practicing free throws. All right, so we want to know what is the probability that the player will make 10 shots before they miss. Now, the first thing that we want to do is define what we're considering a success in this problem. And in this problem, we're considering a success a miss. Okay? That's what we're actually being asked about. And if we look at how it's worded, we want that miss to occur on the 11th trial. Right? Because when we look at the details of this question, it says, what is the probability that the player will make 10 shots before they miss? Right? So we've got 10 makes. Make 10 times, right? 10 makes. And then we have a failure. Okay? Well, if we just set this up using common sense, right, we would say, okay, so 10 makes in a row. Well, they're a 78% free throw shooter. So if they make 10 in a row, we take 0.78, basically raise it to the 10th power. Right? Make, and so on. And then we need a miss. Right? So that 11th trial, when we define n as 11, the 11th shot we want to be a miss. And the probability that they miss is 0.22. Okay? So if we pull our graphing calculators up, so let me pull mine up here, and we calculate this real quickly, right? So we go 0.78 to the 10th power, and we multiply that by 0.22. So we hit enter, and there's our probability. So a very small probability of this free throw shooter shooting 10 or hitting 10 in a row, right? Less than 2% chance. Now, to illustrate, we also have the, again, geometric PDF command on our graphing calculator. So if I go into my distribution menu and I scroll down, right, we know that the binomial distribution is down here. And down below that, you'll see we have a geometric, both PDF and CDF. So I'm going to choose the geometric CDF. My p-value in this problem is 0.22, right? Not the 78%, because remember what we're interested in is a miss, and that's that probability. My x value would be 11. I want that miss to occur on the 11th shot. So I hit paste, and you can see we come up with the exact same probability. So whether you want to treat it as a multiplication rule or you want to use the geometric PDF in your graphing calculator, you can see that either way it works out to give us the same answer. Now let's take a look at the next example. Right, the next example says, what is the probability that the player will make less than 10 shots before they miss? Okay. So this kind of changes things. We're not looking at a specific situation, but we're kind of looking at a range of values. Well, when we start to add in these inequality symbols, things like less than or greater than or at most or at least or more than and so on, okay, that's that inequality symbol. And so what I want to think about is how could I rephrase this using either at least or at most? Well, saying what is the probability that the player will make less than 10 shots, that'd be the same as saying at most 9. And the reason why we want to think about this in an at most phrasing is because that helps us utilize that geometric CDF. Okay? So this means they're going to make at most 9 before they miss. So if I set this up then, that means at most 9. That means at a maximum, I'm going to attempt 10 shots. Right? Now, why am I going to attempt 10 shots? Because we want them to make less than 10 shots. So they're going to make at most 9, but then I need that 10th shot to be that first miss. So if I set this one up in my calculator, I'm going to use the geometric CDF, because again of that at most phrasing, my probability of success would still be the 0.22, and then my n would be 10 in this problem. All right, so if we set this up in our graphing calculator, okay, we'll slide that out of the way so we can see things here. So again, I'm going to go into my distribution menu, and I'm going to go up this time. This is the quicker way to get there. You can see there's my geometric CDF then. So I'm going to choose my geometric CDF. My p-value is 0.22. And again, I want to attempt at most 10 trials. So we're plugging in the 10. We'll hit paste, hit enter, and there's our probability. All right, so there's a 92% chance that that first miss is going to occur in those first 10 shots that they take. Okay, and that kind of matches up to what we see in the probability up above. We don't expect a very high probability of them making 10 shots in a row, right? Let alone 11, 12, 13, or so on. Okay, the last question we have in this example problem is illustrating the mean. So the question here is how many shots would we expect them to make before they miss, all right? Now again, just a reminder, anytime we see that word expect, we want to think average, all right? So on average, how many shots would they make before they miss, right? That's what that phrase expect is saying. Okay, well again, the formula for the mean is just simply 1 divided by the probability of a success. And again, in this problem, a miss is a success. So 1 over 0.22 would be how we would calculate our mean. So if we calculate that out here real quick, pull that calculator back up. So 1 divided by 0.22, that would be how many shots we would expect them to make before they have a miss. Okay? So we'd shoot about 4.5 shots. Okay? A little bit less than 5, which again would make sense, thinking the reciprocal of the probability like we mentioned earlier. Well, that is it for the geometric distribution. Well, let's finish up with just this quick slide here. All right, so if we're comparing the two, notice what they have in common. All right, both geometric and binomial only deal with 2 outcomes. They both deal with independent events. What's different about them is the variable of interest. Right? With the geometric, our variable of interest is a number of trials. How many trials do I have to go through before I experience a success? And in a binomial distribution, the variable of interest is the number of successes within a fixed number of trials. So again, they're both very similar, but we have to be very careful to analyze what's being asked within a question. And as we start to mix these binomial and geometric problems together, that will help us keep those separated out. Okay? Well, that brings us to the end of our Chapter 8, Section 2 video. I hope you guys are having a great day. As always, I want to encourage you to complete the form below the video. And please make note if there's anything that you'd like some more clarification about or have questions on. That's why you need to complete that form. Give me an idea of what we need to address further in class so that we can make sure that you guys are ready to set up and be successful when it comes to geometric distributions. Well, I hope again you guys have a great day, and we'll see you soon.